What's up? I'm Vin, and today I want to go through the June 2022 Algebra 2 Regents. So I'm going through parts 2, 3, and 4, and let's get started. So for this first question here, we want to know, does this equation have imaginary roots, or do we have regular, real solutions here? And we just have to justify our answer, which just means you have to show work. And for a question like this, the first thing that jumps into my head is I immediately think of the quadratic formula, where we have x equals negative b plus or minus. But I think of the plus or minus and this part here, the b squared minus 4ac all over 2a. So, I could write the whole thing out, x equals negative b plus or minus. But once again, the part that jumps out at me is the part under the square root called the discriminant, because the way you determine if you have imaginary solutions is if you wind up with a negative number under the square root. So here, if I had to justify or investigate to justify our answer, what I would say here is I identify we have an a value of 1, we have a b value of negative 4, and we have a c value of 13. So if I investigate b squared, so I have negative 4 squared, minus 4 times a times c. So if we investigate this amount here, this is going to tell us if our roots are real or imaginary. So now we work this out. We have 16 minus 4 times 13 is 52. And now I could use a calculator for this, but I'm just going to do the subtraction on the side here. So I'm just going to borrow, and this is going to work out to 36, but that would be if it was 52 minus 16. We're doing it the other way. So this will be negative 36, which is less than 0. So right away, I see that we have a negative under the square root, which tells us that we have imaginary solutions. So for question 26, we have a lot going on here, but we have a child on a swing, and the first push of the swing sends the child 6 feet, and then we're told each successive swing travels 80% of the distance of the previous swing, and we need to determine the total distance to the nearest hundredth of a foot the child travels in the first 5 swings. So for a question like this, what I'm thinking of is that we're adding up the terms of a sequence, but the million-dollar question here is, what type of sequence are we dealing with? So the first swing is going to go 6 feet, and then it's going to go 6 times 80%. Just know when I hear 80%, I think 80% is the same thing as 80 out of 100. And this fraction reduces to 4/5. So I would just prefer to write this as times 4/5 like this. So this would be the second swing, would be 80% or 4/5 of the first swing. And then it would be another 80%, which means multiply by 4/5 again, which would give us 4/5 times itself, or 4/5 squared. So you could see the trend here. I could add this up 5 times and just keep going down the line like this. Or if you want to use a nice formula here, this is a geometric series, because to get from one term to the next, we're multiplying by 4/5 each time. And the sum of a geometric series, this formula is in the back of the Regents. It's the first term minus the first term times r to the n power over, and then we're dividing by 1 minus r. Let me just fix that. So we have 1 minus r here. Now, what we want to find is the total distance to the nearest foot of the first 5 swings. So that tells us here n is equal to 5. So then to work this out, we would have the sum of the first 5 terms here would be equal to the first term. The first term is 6, minus 6 times r, we already said, is 4/5. So we have 4/5 to the n power, and n is equal to 5. And we're dividing by 1 minus r. So we have 1 minus 4/5. And now the rest of this is just calculator work. So for this one, I want to type in a fraction, so I could press alpha y equals enter. And this is just so I don't have to worry about parentheses as much. So I have on top 6 minus 6 times 4/5 to the 5th power. So we just have to write in parentheses. We have 4 divided by 5. And that part is being raised to the 5th power. And now in the denominator, we had 1 minus r. So we have 1 minus r was equal to 4/5, which we could just write like this. And now we press enter. And notice our answer is expressed as a fraction. So what I could do is I could go to mode, because there's a good chance your calculator is going to be reset when you take the Regents. And we go from auto and we switch it over to decimal like this, because we're going to be rounding this to the nearest hundredth. So notice here we get 20.1696, so we're going to round to 20.17. So we'll just write out our final answer. We have 20.17 feet. So this is the distance that the child swings for the first 5 swings. So for this question here, we just have to do a little bit of algebra. And the first thing I like to think about with these questions is which values of n or x, whatever variable, are not allowed. And one of the most common values to look out for are values that make the denominator of any of the fractions equal to 0. So right away, I look at this and say n is not allowed to equal 0, because I would have 2 over 0, 3 over 0, 4 over 0, and division by 0 is not allowed. So now we're ready to do the algebra. So we're starting off with the original equation here. We have this, And there's a few ways that you could solve this, but one way I like to solve it is I just multiply everything by the least common denominator. So the least common denominator in this case would be n squared, because notice all of these denominators here, if we multiply by n squared, would cancel out in some form. So now what I'll do is I'll distribute this to all three here like this, and now what we have is we have 2n squared over n squared plus 3n squared over n, and this is equal to 4n squared over n squared like this. So now this is going to cancel out. This one will cancel out completely as well, and we'll have 2 plus 3n squared over n. This is going to simplify to n to the first, and this one's going to cancel out completely. So I have 2 plus 3n to the first, or just 3n, is equal to 4. So now from this step, we have 2 plus 3n is equal to 4. We just solve for n, subtract 2 on both sides. And now we've got 3n equals 2, divide both sides by 3. And this will tell you that n is equal to 2/3. Now, if you solve this any other way, one danger you could run into here is you may get n equals 0 as a solution, but I highly recommend that you plug this back into the equation just to make sure that you don't get something undefined for any of the expressions. But n equals 2/3, that's our answer to 27. So question 28 has a little bit of a trap because we're told to factor completely. Now, anytime you encounter the phrase factor completely, that means you're probably going to have to do more than one step of factoring. So if we, let's say, start this off by doing factoring by grouping, what we could do here is we could take out something. Let's say I take out a minus x to the third. Now, I prefer to take out a minus x to the third because I like when my leading term is positive. And if we take out minus x to the third, we're going to be left with, we're going to have 2x minus 1 like this. And now on the second set of terms here, we could factor out a 9x. So we take out the 9x, and here we'd be left with 2x minus 1. So for factoring by grouping, when you have matching leftovers, that means you're on the right track. So now from here, we're going to factor out the 2x minus 1, and that'll bring us to the next line. We'll have 2x minus 1, and then we'll have minus x to the third plus 9x. But if you were to stop here, this is a 2-point question, you would get 1 point. You have to factor completely, which means you have to look at both of these factors and see if any one of them could be broken down anymore. So if we look at these factors here, 2x minus 1 can't be factored any further, but this one can be factored further. And what I want to do is I want to take out a minus x. Now, if I take out a minus x, we'll have 2x minus 1. The minus x I could write over here like this. We have minus x times, and then I'll have positive x squared minus 9. So once again, I like to take out, in this case, a minus because I like when my leading term is positive. And now what we have is a difference of 2 squares. And one thing I could do is I could write the minus x in front because multiplication is commutative. So I have minus x times 2x minus 1. And now this last binomial could factor as a difference of 2 squares, and it'll factor as x plus 3 times x minus 3. So once again, when you hear the phrase factor completely, just be on the lookout that the first factoring you do is probably not going to finish the job. You're going to have more to do. So this would be our original expression factored completely. For question 29, we have a relative frequency table. And given this data, we want to know, are the events of having blue eyes and wearing glasses independent? So for this, and we need to justify our answer. But for this question, what I like to do is I like to come up with a total column here. So if we add up 0.14 plus 0.26, that's going to give us 0.40. And what this tells us is how many people that have blue eyes in this like selection of people here. So 40% of the people have blue eyes, and the blue eye people either wear glasses or they don't. Now the brown eye people are a total of, if we add this up, 35%. And then green eye people make up 0.10 plus 0.15, which is 25%. And notice if you add up these three values here, this is going to work out to 1.0, which would account for everybody involved in this survey. So the last thing I want to add up here is the percentage of people in this collection that do wear glasses. So if we add this and this, 0.14 and 0.11 is 0.25, and you add up this last one, you're going to get 0.35. So that's 35% of the people here wear glasses. And what percent don't wear glasses? If you add this up, it makes up 65%, or 0.65, which completes the other percent here. So now we have enough information to get this going. So first, what we'll calculate is what is the probability of having blue eyes. And if we look here, the amount of blue eye people is 0.40 out of like the whole. So 0.40 out of 1, we could say 0.40 out of 1.00 out of everybody. And this is equal to 40%. But now what we should calculate next is what is the probability of someone wearing glasses and having blue eyes in this section here. So what we're going to do is we're going to limit ourselves to the people that wear glasses. So we're going to limit ourselves here into this column. So what is the probability of having blue eyes given that you wear glasses? So what is the probability of having blue eyes given that you wear glasses? And if we look in this section here, what we have is we have 0.14. That's the probability of having of wearing glasses of the blue eye people out of the total 0.35. And if we work this one out here, this reduces, I imagine dividing by 0.7 on top and bottom. And what this reduces to is 2/5, and 2/5 is the same thing as 40%. So notice what we have here. The probability of having blue eyes is equal to the probability of having blue eyes given that you wear glasses. So this tells us that these events are independent. So for question 30, we just have a lot of algebra to do. And what I would do to the left side here is I would break this up and say this is the cube root of 81 times the cube root of x to the 15th power times the cube root of y to the 9th power. So that's how we could rewrite the left side. And that's going to be equal to 3 to the a, x to the 5th, y to the 3rd. But now the next thing that you need to know is that when we write an expression in radical form, we could write it as a numerical exponent if we use this idea of power over root. So the cube root of x to the 15 is equal to, and let me just make this a little bit thinner, is equal to x to the 15 over 3. It's equal to x to the power over the root. And x to the 15 over 3 simplifies to x to the 5th power. So now I could rewrite this as cube root. And 81 I'm going to write as 3 to the 4th power. And you'll see why in a moment. So I have the cube root of 3 to the 4th power. And now we have the cube root of x to the 15 is x to the 5th power by the same thought process we just used here. And now same idea, this part we'll do in our head, but this is going to be equal, times y to the power over the root. And if I do 9 divided by 3, that's 3. So that gets us here, and this is equal to 3 to the a power, x to the 5th, y to the 3rd. But now notice I have matching x to the 5ths, and I have matching y to the 3rds. They told us here x is non-zero and y is non-zero. So that means we're allowed to divide both sides by x to the 5th, y to the 3rd. So that's just so that we're not dividing by 0, that they have to tell us to assume this. And now x to the 5th cancels, y to the 3rd cancels on both sides. And that gets us here. But now remember that power over root idea. This I could rewrite as 3 to the power 4 over the root 3. And now that's equal to 3 to the a. But notice we have matching bases. So the only way these two will be equal is if their exponents are the same. So a is equal to 4/3. And this is our solution to question 30. So question 31, we just have to graph this equation here over the interval from 0 to 2 pi. Now, the calculator is amazing for doing graphs, but it's very important that you have a strong foundation in some of these topics so that you know what to tell the calculator. So the first thing that jumps out at me for a question like this is I think cosine x on its own looks like this. It starts at 0, 1, and it just starts its wave like this, and it goes from 1 to -1 like this. And it also goes that way as well. But if I were to throw a 2 in front, a 2 would make it go from up to 2 and down to -2 like this. So that just makes the graph taller, and it makes it go lower like this. It affects the amplitude. And now if I throw in a +5, that means the high and low points are going to be 2 plus 5, which is 7. And then I would have -2 plus 5, which is equal to 3. So that's just what I'm expecting when I graph something like this before I tell the calculator anything. Now, another thing I look out for, and then we'll get to the calculator, is I like to evaluate cosine at 0, because cosine of 0 is 1. Cosine at pi over 2 is equal to 0. Cosine of pi is equal to -1. Cosine 3 pi over 2 is equal to 0. And then cosine of 2 pi brings you back to 1. So these are just some values I'm on the lookout for. So let's go to the y equals here, and we'll type in our function. We have 2 cosine of 1/2 x, so we'll just use 0.5 here for 1/2. And then at the end, we're just tacking on a +5. Now, if you graph this, you'll get a rough idea of what this thing looks like. And notice we're in radians here to get the full picture. And the problem is, though, we have a lot of wasted space, and we're not keeping to the interval they gave us. So what I would do first is switch the x minimum to 0 and the x maximum to 2 pi, And remember the pi button, we're going to press second and this up arrow here to throw in a pi. And that gives us the piece that we need. But notice there's a lot of wasted space down here in quadrant 4 because the graph is all in quadrant 1. So what I could do is I could switch the y minimum to 0 because we don't need to go down into the negative here. And that's going to keep us all in quadrant 1. So this is a better picture for us. Now, one other thing to be mindful of here is that we went from 0 to 2 pi, but we could press second window here, and the graph they gave us on the test paper goes from 0 to 2 pi, but there were 10 spaces to get there. So what you could do is you could take 2 pi and you could divide it by 10. And now when you go to the table of values here, notice we have 0, 7, 3.14, 1, blah, blah, blah. That's pi. So this gives us the whole numbers. We have 0, pi, and 2 pi give us the nice values that we could use. So we'll use this from the calculator to help guide our graph. But just know a common mistake that I see is students will just do their best to just draw something random and hope the person grading it is just going to give them credit for drawing what they saw in the calculator. But you have to be careful here. Notice that we were counting by 10 spaces and we're going from 0 to 2 pi. So that's why I counted by 2 pi divided by 10. But the only values that are easy to see are from 0 to 7. So I'm sorry, 0 comma 7. So we're going up 1, 2, 3, 4, 5, 6, 7. So that would be here at 7. And then next we would have 3.14. That's really just pi in disguise. So pi comma 5. And we're going out 1, 2, 3, 4, 5 spaces. Remember, pi was the halfway point. Here's 0. And we're ending at 2 pi. So at pi, we're going up to 5, which is 2 below this point here. And then at 2 pi, we're down here at 3. So that's going to put us over here. And when we sketch this, we're going to draw this in a wave-like fashion. So this is like the decreasing part of the wave. And then this is the part here that goes under like this. All right. And if we want to use some of the vocabulary, remember 7 would be the max. And then the min value would be 5. I'm sorry, would be 3 because we're going down to 3 here. The midline would be at 5. So this at 5 would count as the midline. You don't have to label all this on the Regents, but all this information here will just help you produce the best picture you possibly can for 31. Question 32 is easy if you know how to type this into the calculator, and what we want is an exponential regression equation, and we're naming the equation f of t. So we'll just switch back to the calculator view here, and we're going to go stats, and we're going to edit our table here. So we're going to just fill up this column here with everything from the question. So L1 is our column for t, and L2 is our column for f of t. And now what we want to do is we're going to go to stats, and we're going to go to calculate over to the right here. And we're going to go to exponential regression, which if you scroll down is number 0 here. This is the abbreviation for exponential regression using L1 and L2. So we just go ahead and do this, and this is the information we need to answer this. So now just borrowing this information, please make sure though that if they tell you to name this function f of t, don't use y and x, use f of t. And then instead of x, use t. So here we're rounding to the nearest thousandth, and we have to look here. The coefficient of our exponent term a is 169 point, and then we have 136, and we're rounding to the nearest thousandths place, so we stop 3 decimals after. The 0 tells us to round down to 136, and now we just go ahead and throw in our parentheses here. Inside the parentheses, the base of our exponent is we have 0.971. And we stop here because this is the thousandths place, and 1 unit to the right here is a 1, so we're rounding down. And now remember, we're not going to tack on x, we're going to say to the t power here because this is a function of t. So question 33 is 2 parts. First, we're going to graph these 2 functions, and then we're going to state the number of solutions to f of x equals g of x. So we'll go back to the y equals here, and first we'll type in f of x. F of x was x to the 3rd power. So we have x to the 3rd, and then we have minus 3x squared. So we'll just tack that on here. And then after this, for g of x, we have 2x minus 5, which is just a linear function here. So this is what we need, and we'll press zoom 6 because we adjusted the window before. Pressing zoom 6 puts everything back to normal. Now, another thing worth looking into here, also we should press second window. Remember, we were counting by pi, 2 pi over 10 before. So I'm going to clear this out and go back to counting by 1. So delta table just tells you what to count by in the x values. And now when we go to the table here, we'll have some values that we could use. And I stay in the neighborhood of the values where the y values aren't too far out of control. And if we look at a picture of this, notice right away for the second part, I could already see that we have 1, 2, 3 solutions because there are 3 points where these 2 graphs intersect. So now we'll use the table and the graph to help us out. So this would be for f of x, and the one in red is for g of x. So now we'll just go ahead and graph these. F of x, that's our cubic function. We have the point 0, 0, and then we have the point 1, negative 2, which is down here. And then we have the point 2, negative 4. So we're going over 2, down 1, 2, 3, 4. And what I notice also is that 2, negative 4 looks like the turning point here. And then 3, 0 is the next point. So we're going over 1, 2, 3, and to the x-axis here. And then 4, 16 would send us way, 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 way up. So we're not going to go any more to the right. If you go to the left, negative 1, negative 4, so going down 1, 2, 3, 4, is a significant point that we could graph. So if I'm drawing this out, I'm going to make sure I plot points that are very well defined within this space. And now I just do the best I can with my limited artistic ability to connect these. So we have this one goes here, then it loops, and then it goes up. Okay, it's going way, way, way up to, we're heading towards 416. But the table is what will make this more forgiving, plus your 5, in this case, yeah, we have 5 well-defined points. And let me just make that arrow a little bit clearer. Now for the linear function, this one is easier to graph because 2x minus 5, I could just go down 1, 2, 3, 4, 5. And you could even see here 0, negative 5 is a point. And now I'm just using the slope. I'm going up 2 over 1 like this. So we're going in this direction here like this. And this will give us the graph for the line. And then here I go down 2 over 1. So we're going down 2 over 1 like this. And now I just connect these. And I'll make that a little bit neater. So let's try that one more time. So we're going here like this. So 1. And I'll do this in pieces just in case I mess up, that I don't erase the whole line a second time. And what I'll do is I'll extend this blue one here to show that these are clearly intersecting at 3 locations. So notice we have 1, 2, 3 points of intersection. So for this last part, we just have to state the number of solutions. So notice there are 3 solutions here because the graphs have 3 points of intersection. Now, I know they didn't tell us to explain our work here, but just in case they ask you to explain, this would be a full sentence that would explain why we have 3 solutions. Now, question 34 has a lot going on, but all we really need out of this is we have this equation for t equals, where t is time, capital L is the length of a pendulum, and g is a constant for gravity. That's 9.81 meters per second squared. And we're told the first Foucault pendulum, I hope I'm saying that right, was constructed in 1851, and here's some important information. The pendulum had a length of 67 meters. And now the actual question is to determine to the nearest tenth of a second, and let me not cross it all out, the time that it takes the pendulum to complete one swing. So here, what we have is we're just plugging in. We have capital L, in this case is 67 meters. And we're told here, it's a little bit sneaky, but lowercase g, they told us, is 9.81 meters per second squared. So if you're taking physics, then this will be easier to recognize, but otherwise they're telling you the value for gravity here. So if we calculate t, for the first part of this question, it's not so bad. We're just doing 2 pi times the square root of capital L is 67 meters, and we're dividing by g, which is 9.81 meters per second squared. But instead of, I mean, you could write the units in here, meters over meters per second squared, but you could just also leave a space and tack on seconds at the end to show like time is going to give you seconds. But the units would cancel out to give you seconds anyway. Now the rest is just typing this in the calculator and rounding to the nearest tenth. So let's just go back to the main page here. So we have the expression 2 pi, so second up arrow here, and then we have the square root of 67 divided by 9.81. So this is, once again, just all calculator work. And we're rounding this to the nearest tenths place. So to the tenths place is a 4, to the right is a 2. So we're rounding this down to 16.4. So this tells us t is equal to 16.4 seconds. So this is our solution to the first part. For the second part of this question, we have the equation from the beginning, t equals, and we had 2 pi times the square root of capital L over g. And this time around, what we want to do is we want to determine to the nearest tenth of a meter the length of the pendulum. So this time we're solving for L, and we're told this time that t equals 9.6 seconds. So this is a given piece of information here. So what we'll do is we'll just write it without the units, and we'll write the units at the end. So what I would do is we have 9.6 equals 2 pi times the square root of capital L over g. But remember, g we have a specific value for is 9.81 meters per second squared. So, and make sure that you extend the square root so that it includes L and this denominator here. So now to solve for capital L, I would start by dividing both sides by 2 pi. So we have divide by 2 pi on both sides. And now that brings you to this step. We have 9.6, and I'll just color code this a little bit different so it stands out. We have 9.6 over 2 pi equals the square root of L over 9.81. And now what we'll do is we'll square both sides because that'll get the square root to disappear. And the next stage over here, what we have is we have L over 9.81. So that breaks the square root equals, and I'm just going to leave it like this, 9.6 over 2 pi squared. And now to solve for L, we're just going to multiply both sides by 9.81. So we have 9.81 being multiplied across. And this is going to tell us L equals, and we'll have 9.81 times, and in parentheses, we have 9.6 over 2 pi, and this is being squared. And the rest is calculator work. Now, before we type this in, I just want to point out a common mistake. Please get out of the habit of writing expressions like this. Like if you were to write 9.6 divided by 2 pi like that, the problem with this is the calculator will do 9.6 divided by 2 and then multiply by pi. What you should be doing is you could put this as a fraction, 9.6, and then divide by 2 pi like this. Or what you could do to resolve that issue is you could take this expression here and you could throw the 2 pi in the denominator, but just make sure you throw it in parentheses, okay? Because that's, once again, I see students make that mistake all the time, and it's devastating if you know what you're doing, but you just make a typo. So now we'll just type in what we had. We had 9.81 times, and in the parentheses here, we have the fraction. We have 9.6 divided by 2 pi, and this fraction was being squared. So once I get out of this fraction and close the parentheses, I'm just going to tack on a square. And this is going to round to the nearest tenth to 22.9. So capital L is 22.9 meters. And here's our solution to the rest of question 34. For question 35, there's a ton to read, but for questions like this, there's just a few things that pop into my head. I know this is the standard deviation question referring to the middle 95% of the data. So automatically what I think of is plus or minus 2 standard deviations, where if we look at a bell curve here where the average is in the middle like this, what we mean by that is if we go 2 standard deviations to the right and we go 2 standard deviations to the left, the 95% refers to the bulk of the data, which is in this section here. So that's automatically what I'm thinking of when I read this type of question. But now I have to get context here, that in order to, we have decreased the percentage of residents who drive. So the city is launching a campaign to encourage people to use public transport instead. All right, so that's the goal of this study here. And what we have is before the campaign, the city estimates that 65% of the residents drive to work. So this is a significant number here. We're going to need that later. And the simulation was run, and now here's all the information we have. For the first part of this question, we have to construct an interval containing the middle 95% of the data based on the simulation, and we're rounding to the nearest hundredth. So for this one, once again, I'm just thinking plus or minus 2 standard deviations, but remember, we're always starting at the mean, the average, which is right in the middle. So here, our left endpoint would be the average, 0.651, but we're subtracting 2 standard deviations like this. So this is going to give us the beginning of our interval. So we have 0.034. Let me just make that a little bit neater. Actually, I'll just backtrack a bit. So we'll just make that look a little bit better. And now for the right hand, we have the average plus 2 standard deviations. So the average is still 0.651, and now we're adding 2 standard deviations like this. So then this is just all calculator work here. If you type this in for the first part, rounding to the nearest hundredth, what we'll have is we'll have 0.58. And then if we do the average plus 2 times the standard deviation, the right endpoint would give us 0.72. And once again, we're rounding to the nearest hundredth. Now for the second part of this question, we have 1 year after launching the campaign, the Department of Transportation conducts a survey of 200 randomly selected residents, and they find that 122 of them drive to work. So we want to look here, should the department conclude that the city's campaign was effective? And we have to use the statistical evidence from the simulation to explain our answer. So for this one here, the first thing I would do is just do 122 out of 200. And this is going to be equal to, if we reduce this, we could say 61 over 100, which is 0.61. Now, there's a very, very, very dangerous trap here. If you're not careful, you'll look at this and say, wait a minute, 0.61, that's between 0.58. So I'll just write this out. This is between 0.58 and 0.72. So yes, yes, yes. And you just fall into that trap. But be careful. What we wanted here, the goal of the Department of Transportation was to reduce the amount of people that drive to work. So this was 1 year ago, and this is 1 year later that we have this percentage. So that's actually a bad thing that the percentage of people driving fell within this interval here, because if the goal was to reduce it, it would have to be less than 0.58 for the campaign to be effective. Question 36, we're solving this system algebraically, which means we can't use a calculator. But it does help to know how to graph basic functions like this, because what it could do is it could help you visualize this so you know what your answer should look like. So x squared plus y squared equals 25 is a circle of radius 5 centered at the origin. And if I look at this line, y equals, and in my head I'm just saying y equals 2x minus 5. I'm just solving for y. This would be a line that starts at 0, negative 5, and has a slope of 2. So let me just make that a little bit neater. So it's going up like this. So right away, I know I'm going to have two solutions based on how this was drawn. But just know I could have had a situation where I have a circle and a line where it completely misses, or you could have a circle with a line tangent and you would only have one solution. But this is a two-solution situation. So what we could do here is we could solve this for y. We could say y equals, if we subtract 5 on both sides, we have 2x minus 5. And now what we could do is we could plug this into the first equation. So we're solving the system by substitution. So we'll have x squared plus, and instead of y squared equals 25, we're replacing y with 2x minus 5. Now, another thing I think about here, if you could do this in your head, then great, but 2x minus 5 squared is actually 2x minus 5 times 2x minus 5. So we have 2x times 2x. The first term that comes out of this is going to be 4x squared. But then you have to be careful. We're doing 2x times negative 5 is negative 10x. And then you do negative 5 times 2x is another negative 10x, which makes negative 20x. So if you could do this in your head, then great. But otherwise, there's no harm in just showing the work. But then minus 5 times minus 5 is plus 25. And this all equals 25. So this is actually a nice case because the 25s just cancel out like this. So we could just do minus 25 and cancel this stuff out. And now on the next line, we could combine x squared plus 4x squared is going to give us 5x squared, and then we have minus 20x, and now everything here is equal to 0. So from here, we could just do factoring out the greatest common factor. So we could take out a 5x, and we'll be left with x minus 4, and this is all equal to 0. So from this stage here, we're going to get two roots. We'll have 5x equals 0, which implies x equals 0 is one solution, and then we have x minus 4 equals 0, which tells us x equals 4. But in order to get full credit, we need corresponding y values with each x value. So we could say here, when x equals 0, I would plug into this y equals, because that's like the most direct here. If we have x equals 0, we'd have y equals 2 times 0 minus 5, which gives us y equals negative 5. So our first solution is going to be, we could say 0, negative 5. And now the second solution we would get by substituting in x equals 4, and that would give us y equals 2 times 4 minus 5, and this is going to give us 8 minus 5, which is equal to 3. So our second answer is going to be the 0.43. So we could just box this off and label it, but here are the solutions for this question here. All right, so we made it to part 4. Here's the final boss, and it's worth 6 credits. So for question 37, we have the population of the US represented by a recursive formula. And A naught, or A sub 0, represents the population in 1910, and N represents the number of years since 1910. And now here's the first part of this question. Identify the percentage of the annual rate of growth from the equation, and we have A sub N equals this here. Now for this, it helps to come to the Regents with some background knowledge, and the background knowledge you need for something like this is I just think of this formula that we have the principal amount times 1 plus or minus the interest rate to the t power. And in this case, because it's population growth, it would be plus. So that's automatically what my brain shifts to. So when I think about this question, one of the next things that jumps out at me is when I look at the recursive formula, I look at the coefficient, which is 1.015, and I notice 1.015 is equal to 1 plus 0. And we have 0.15 like this. So that tells me what R is. R is equal to 0.015. So here, identify the percentage of the annual rate of growth. This is 0.015, which is the same thing as 1.5 out of 100. If you needed to convert this to a fraction, you could just press math, enter, enter. But just know this as a percentage, 1.5 out of 100 is the same thing as 1.5%. So this would be the percentage here. And once again, the idea is that to find the new population each year, you just multiply the previous year by 1.015, and that puts in the percentage growth. So now we have to shift our focus and write an exponential function, p, where p of t represents the population in millions of people. And t is the number of years since 1910. So for this one here, we could use this helpful form and see that p of t is equal to, and we had the initial population is 92.2. So that p value in front always represents the initial amount or population. So we have 92.2 times the rate of growth plus 1. So we have times 1.015 like this, and it's a function of t, so we just throw on that exponent in terms of t. So for the final part here, we're going to use this model for p of t, and we're going to determine algebraically the number of years, which tells me right away we're solving for t. But we're solving for the number of years it takes the population to reach 300 million people, and we round to the nearest year. So for this, we're just going to let p of t equal 300, and we're setting this equal to 92.2, and we have 1.015 to the t power. So from here, this is all algebra. So we're going to divide both sides by 92.2, and that's going to get the exponential term by itself. So that brings us here. We have 300 over, and we have 92.2 equals, we have 1.015 to the t power. Now, a common mistake here is people try to divide by 1.015, and they cancel it out and think they're done. But just know, this is an exponent. So t is not being multiplied by 1.015. It's the exponent of this base. So that means we have to do a different operation, and the opposite of exponentials is logs. So here you could pick your favorite log. Mine happens to be natural log, so I would take the natural log of both sides like this. So we take the natural log of both sides, and then where my head goes after this is I think of log properties. That when we have something like natural log of, let's say, a to the b power, that b could come out in front and become b times natural log. I started to write regular log, so b times natural log of a. So that's the algebra I want to use here, is that t is going to come out. And what we're going to have is we have ln of 300 over 92.2 is equal to, and we'll have t times natural log of, and we have 1.015 left. So now from here, to solve for t, just divide both sides by natural log of 1.015. So we could say here that t equals, and we have this messy expression, so 300 over 92.2, and we divide by natural log of 1.015. Just know, once again, this would have worked if we used log, but I just happen to pick natural log. So we could just type this in. We have alpha y equals enter to pull up a fraction, and on top we had natural log of 300 divided by, and we had 92.2. And then in the denominator, we also had natural log, but we had natural log of 1.015 like this. So now rounded to the nearest year, we're going to go with 79 years because the 2 tells us to round down to 79. So once again, rounding to the nearest year, we have t equals 79 years.